The problem was the wires, not the transistors, not the resistors, not the capacitors. The wires that connected them, the hair-thin copper conductors that a skilled technician had to solder between each component, one connection at a time, in a process that was slow, expensive, error-prone, and fundamentally incompatible with the direction that electronic technology needed to go if it was going to fulfill the promises that its advocates were making about it. In 1958, the most sophisticated electronic systems in the world, the computers that filled rooms at universities and research laboratories, the guidance systems that the military was developing for ballistic missiles, the communication systems that connected military command structures, were assemblies of discrete components. Transistors, resistors, capacitors, and inductors, each one a separate physical object, each one connected to the others by wires that a human being had to solder in place. The transistor had been a revolution. Invented at Bell Telephone Laboratories in 1947, it had replaced the vacuum tube as the basic switching and amplifying element of electronic circuits, replacing a device that was large, fragile, power-hungry, and unreliable with a device that was small, solid-state, efficient, and durable. The transistor had made portable electronics possible, had made reliable computers possible, had made the entire range of applications that electronic technology was being asked to serve more practically achievable. But the transistor had not solved the wiring problem. A circuit that required 100 transistors required 100 transistors to be wired together, plus whatever resistors and capacitors and other components the circuit needed, plus the wires connecting all of them. The size of the circuit was the size of its components plus the size of their interconnections. The reliability of the circuit was limited by the reliability of its weakest solder joint. The military understood this problem with specific clarity because the military was trying to build systems, missile guidance computers, airborne electronics, communications equipment, that required hundreds of thousands of components in packages small enough to fit in aircraft and missiles and field equipment. The weight and volume of the interconnections was, in some applications, as significant as the weight and volume of the components themselves. The military was paying people to solve this problem in 1958. The solution that emerged was not the solution anyone had been trying to build. America in 1958 was in the middle of a technological crisis that the Soviet Union had created. Sputnik had been launched on October 4, 1957, and the psychological impact of the Soviet Union placing a satellite in orbit before the United States had done so was not primarily about the satellite itself. It was about what the satellite implied, that the Soviet Union had developed rocket technology capable of placing a payload in orbit, which meant rocket technology capable of delivering a nuclear warhead to any point on the Earth's surface. The American military's response to Sputnik was a comprehensive reassessment of its technological programs, a systematic examination of what the Soviet Union could do that the United States could not, what the United States could do that the Soviet Union could not, and what needed to change to ensure that the balance of capability remained in America's favor. The electronics problem was high on the list. The guidance computers for ballistic missiles, the electronic systems for the aircraft that would deliver or intercept nuclear weapons, the communication systems that would coordinate military response in a crisis. All of these were limited by the size, weight, and reliability constraints of discrete component electronics. The military needed smaller, lighter, more reliable electronics than discrete components could provide. The Defense Advanced Research Projects Agency, DARPA, established in February 1958 as a direct response to Sputnik, was funding research on the miniaturization problem from multiple angles. The military's various service branches had their own miniaturization programs. The electronics companies that supplied military equipment were working on the problem independently and in response to military contracts. Texas Instruments was one of those companies. Texas Instruments had been founded in 1951 by Patrick Haggerty, Cecil Green, and Eric Johnson as a spin-off from Geophysical Service Incorporated, a petroleum exploration company that had developed expertise in electronics during its work on seismic instruments for oil exploration. The company had made its first major mark on the electronics industry in 1954, when it produced the first commercial silicon transistor, and the same year the first transistor radio, the Regency TR1, developed in collaboration with the Industrial Development Engineering Associates. By 1958, Texas Instruments was a significant player in the semiconductor industry, producing transistors for military and commercial customers, and pursuing the research that would allow it to compete with the established electronics companies General Electric, Westinghouse, RCA, that had built their positions in the tube era and were transitioning, with varying degrees of success, to the transistor era. Jack Kilby arrived at Texas Instruments on May 1, 1958. Jack St. Clair Kilby was 34 years old when he arrived in Dallas, a native of Great Bend, Kansas, who had spent the previous decade working for Centralab, a manufacturer of electronic components in Milwaukee. Kilby had studied electrical engineering at the University of Illinois, graduating in 1947, and had spent his decade at Centralab working on miniaturization problems, specifically on the ceramic wafer assemblies that Centralab was developing for hearing aid electronics. The hearing aid was the consumer application that most aggressively demanded miniaturization in the early transistor era. The person wearing a hearing aid needed the electronic components to be small enough to fit behind an ear or inside an ear canal, which pushed the limits of what discrete component assembly could achieve. Kilby's decade of working on hearing aid miniaturization had given him a specific and practical understanding of the limits of discrete component assembly. He knew what could be made smaller through better manufacturing processes and what could not be made smaller regardless of how good the manufacturing was. He knew where the fundamental limits were. He had also been thinking about a different approach, not making discrete components smaller, but eliminating the discrete component concept entirely. His thinking had been developing in the years before he joined Texas Instruments, informed by his work at Centralab and by the published research literature on semiconductor physics. The thinking had a specific form. What if all of the components of a circuit, not just the transistors, but the resistors and capacitors as well, could be made from the same semiconductor material, in the same manufacturing process, on the same piece of semiconductor? If all the components were made from the same material in the same process, they would not need to be connected by wires after manufacturing. The connections could be part of the manufacturing process, could be formed in the semiconductor material itself, as conductors created by the same techniques used to create the transistors and resistors. No wires, no solder joints, no assembly. The entire circuit would be a single piece of material. This was the idea that Kilby arrived at Texas Instruments with in May 1958. He did not have it fully worked out. He did not have a specific design. He had the concept, the recognition that the wiring problem could be solved not by making wires smaller or more reliable, but by eliminating the need for wires entirely. He arrived at Texas Instruments during the 2 weeks in July when most of the company's employees were on vacation. Kilby was new and had not yet accumulated the vacation time to take the 2 weeks off. He stayed at the laboratory. In the empty laboratory, in the 2 weeks when nobody else was around, Jack Kilby worked out the integrated circuit. The notebook entry that documented his thinking is dated July 24, 1958. The entry is brief, a few sentences and a sketch, but it contains the essential concept. Kilby wrote that it appeared to be feasible to make all circuit components on a single monolithic crystal of silicon. The components would be formed in the silicon by the same diffusion and deposition processes used to make transistors. The connections between components would be formed on the surface of the silicon. The result would be a complete circuit in a single piece of semiconductor. The entry describes what we now call the integrated circuit, the concept that would become the foundation of modern electronics, the concept that would eventually allow billions of transistors to be placed on a chip the size of a fingernail, is present in Kilby's July 24 notebook entry in its essential form. The entry was not an accident in the sense of being random or unintended. Kilby had been thinking about the problem systematically, had arrived at a specific approach, and had written down his conclusion. The accident, if the word is appropriate at all, was in the specific conditions that produced the insight. The 2 weeks of vacation that left Kilby alone in the laboratory, without the daily demands of ongoing projects, without meetings and administrative requirements, provided the uninterrupted thinking time that allowed the concept to crystallize. The laboratory being empty also meant that Kilby had access to the equipment and materials he needed to begin testing the concept without having to negotiate for resources with colleagues whose priorities might differ. He began building a prototype immediately. The prototype used germanium rather than silicon. Germanium was the semiconductor material that Kilby was most familiar with from his Centralab work, and using a familiar material allowed him to focus on the circuit concept rather than on the properties of an unfamiliar material. The circuit he built was the simplest possible demonstration of the integrated circuit concept, a single oscillator circuit consisting of a transistor and the resistors and capacitors required to make it oscillate, all formed in a single piece of germanium. The demonstration was set for September 12, 1958. Texas Instruments management, Haggerty and the other senior executives gathered in the laboratory to watch Kilby connect a power supply to the germanium chip and observe the output on an oscilloscope. The oscilloscope showed a sine wave. The circuit was working. Robert Noyce was working on the same problem at Fairchild Semiconductor in California, and his solution arrived approximately 6 months after Kilby's. The simultaneous independent invention of the integrated circuit by Kilby at Texas Instruments and Noyce at Fairchild is one of the most discussed cases of parallel discovery in the history of technology. The specific situation where two people, working independently and without knowledge of each other's work, arrive at the same fundamental concept within months of each other. Noyce was 30 years old in 1958, a physicist from Grinnell, Iowa, who had co-founded Fairchild Semiconductor in 1957 with 7 colleagues, the traitorous 8, as they were called, because they had left their previous employer, William Shockley's semiconductor laboratory, to start the competing company. Noyce had been thinking about the miniaturization problem from a different angle than Kilby. Where Kilby had focused on the concept of making all components from the same semiconductor material, Noyce focused on a specific manufacturing technique, the planar process that Gene Hoheney at Fairchild had developed, that allowed all of a transistor's features to be formed on the flat surface of a silicon wafer rather than at different depths within the material. The planar process had a specific implication that Noyce recognized. If all of a transistor's features were on the flat surface, the connections between transistors in a circuit could also be formed on the flat surface, using metal deposited on top of an insulating layer of silicon oxide. The metal connections would not be wires soldered between components. They would be part of the manufacturing process, formed on the wafer surface with the same precision as the transistors themselves. Noyce wrote his notebook entry describing the interconnected planar circuit in January 1959, approximately 6 months after Kilby's July 1958 entry. His design had specific advantages over Kilby's approach: the use of silicon rather than germanium for better high-temperature performance, and the planar interconnection technique that was more compatible with manufacturing at scale than the wire bonding technique that Kilby's first prototypes had used. The patent dispute that followed, Texas Instruments filing for a patent on Kilby's concept, Fairchild filing for a patent on Noyce's implementation, occupied lawyers for a decade before being resolved in a cross-licensing agreement that allowed both companies to use both sets of patents. The resolution acknowledged that both men had made essential and independent contributions to the invention of the integrated circuit. The resolution is historically accurate. Kilby invented the concept. Noyce invented the manufacturing approach that made the concept commercially viable. Neither invention was complete without the other. The first commercial application of the integrated circuit was not the military system that the military's miniaturization programs had been designed to produce. Texas Instruments had been working on military applications from the beginning. The Minuteman missile guidance computer was an early integrated circuit customer, and the military's willingness to pay premium prices for the performance advantages that integrated circuits provided was an important factor in funding the early development of integrated circuit manufacturing. But the specific commercial application that brought integrated circuits to the mass market was the hearing aid. The connection was not coincidental. Kilby's decade at Centralab had been spent on hearing aid miniaturization. His understanding of the limits of discrete component assembly had been developed in the context of hearing aid electronics. The concept of the integrated circuit had emerged, at least in part, from thinking about the specific constraints of hearing aid design. Texas Instruments' first commercial integrated circuits were sold to hearing aid manufacturers in the early 1960s. The circuits allowed hearing aids to be made smaller and more reliable than anything achievable with discrete component assembly. The commercial success of the hearing aid market provided revenue that funded continued development of integrated circuit manufacturing processes. The irony was specific. The technology that would eventually allow the construction of the most complex electronic systems ever built, the microprocessors of modern computers, the communication systems of the Internet, was initially deployed in devices designed to help people hear the world around them. The development of the integrated circuit into the microprocessor, the single-chip computer that would eventually run everything from pocket calculators to smartphones, took approximately a decade from Kilby's 1958 demonstration. The intermediate steps were the development of manufacturing processes that could place more transistors on a single chip with greater reliability. Each generation of manufacturing technology allowed transistors to be made smaller, which allowed more of them to fit on a chip of a given area, which allowed more complex circuits to be integrated on a single chip. Gordon Moore, who had been one of Fairchild's founders and who would later co-found Intel with Robert Noyce, observed in 1965 that the number of transistors on an integrated circuit was doubling approximately every year. He projected that this trend would continue. The projection, which became known as Moore's Law, proved accurate for decades, though the doubling period extended from 1 year to approximately 2 years as the manufacturing challenges of making transistors smaller became more difficult. Moore's Law was not a physical law. It was an empirical observation about the pace of engineering progress in semiconductor manufacturing. The engineers who were developing the manufacturing processes that drove the trend were not constrained by Moore's Law. They were creating it through the systematic application of research and capital to the problem of making transistors smaller and more reliable. Intel, founded by Noyce and Moore in 1968, produced the first commercially available microprocessor, the Intel 4004, in 1971. The 4004 placed 2,300 transistors on a single chip, a circuit that would have required 2,300 individual transistors, plus resistors, capacitors, and the wiring to connect them all in discrete component form. On the Intel 4004, all 2,300 transistors were on a chip the size of a thumbnail. The 4004 was designed for a Japanese calculator company, Busicom, that needed a computer on a chip for its calculator products. The specific application was not the grand vision of a computer for every person that the microprocessor would eventually enable. It was a calculator application, a practical commercial problem that required a specific technical solution. The accident, if the word applies, was in the generality of the solution. A microprocessor that could be programmed to perform calculator functions could also be programmed to perform any other computational function. The calculator application was the occasion for the invention. The invention was general. Jack Kilby received the Nobel Prize in Physics in 2000, sharing the award with Georges Ulfarov and Herbert Kromer for their contributions to semiconductor technology. The Nobel citation acknowledged Kilby's invention of the integrated circuit as the foundational achievement that the award recognized. The prize committee's description of the integrated circuit's impact, the technology that enabled the information age, that underlies every digital device, that is the basis of the computers and communication systems of the modern world, was accurate and understated simultaneously. Kilby was 76 years old when he received the Nobel. He had spent the years since his 1958 invention at Texas Instruments, working on applications of integrated circuit technology and contributing to successive generations of semiconductor development. He had received numerous other recognitions: the National Medal of Science from President Johnson in 1969, the National Medal of Technology from President George H.W. Bush in 1990. But the Nobel, coming 4 decades after the invention it recognized, was the acknowledgement that the broader scientific community gave to an engineering achievement whose significance had been understood by the electronics industry since 1958. Robert Noyce died in 1990, 10 years before the Nobel was awarded. The Nobel Prize is not awarded posthumously, and Noyce's co-equal contribution to the integrated circuit's invention was acknowledged in the Nobel citation's description of the award, but could not be recognized by the prize itself. The hearing aids that had motivated Kilby's decade at Centralab and that had been among the first commercial applications of the integrated circuit are still manufactured, though the integrated circuits in modern hearing aids bear no physical resemblance to Kilby's germanium prototype. Modern hearing aid processors contain millions of transistors on chips that are fractions of a millimeter in size. The wires that were the problem in 1958 are gone, not from hearing aids, from every electronic device in the world. The integrated circuit eliminated the need for wires between components by incorporating the connections in the manufacturing process, and the manufacturing process has been refined over 6 decades to the point where the connections, the metal conductors that link transistors within a chip, are measured in nanometers rather than millimeters. The chip that Kilby demonstrated on September 12, 1958, the germanium oscillator circuit that produced a sine wave on an oscilloscope in Texas Instruments' Dallas laboratory, is preserved at the Smithsonian Institution's National Museum of American History in Washington, D.C. It is small, a sliver of germanium, a few millimeters on each side, with gold wire bonds connecting the components. It is fragile-looking, the kind of object that would be easy to overlook if you did not know what it was. It is what it is, the first integrated circuit, the device that solved the wiring problem by eliminating the wires, the invention that made possible every digital device that has been built since, the computers, the smartphones, the servers, the controllers in aircraft and automobiles and medical devices, the communication systems that carry information across the globe. All of it descended from a 2-week July vacation in Dallas, an empty laboratory, a notebook entry dated July 24, 1958, and a new engineer who had been thinking about hearing aids for a decade. The wires were the problem. The chip was the solution. That was the whole job. It was more than enough.